All right, so how do you get these AI agents who are totally self-interested, right? I mean, they're programmed only to get the most points for themselves. How do you get them to actually cooperate? For years, the answer always seemed to be, these super complicated handcrafted rules. But what if the secret to getting them to work together isn't in the code at all, but in how you teach them? Let's dive into how a better education can teach a selfish agent to be a real team player. Okay, so the core of this whole thing is a classic puzzle from game theory, something called the prisoner's dilemma. Just take a look at this chart here. If two players cooperate, they both do pretty well. If they both turn on each other, defect, they both get zip, nothing. But here's the kicker, the real temptation. If you defect while the other player cooperates, you get the absolute biggest prize, and they get totally burnt. And that right there, that's the paradox. I mean, if you're being purely rational, just looking out for number one, defecting always looks like the smartest play, no matter what the other person does. And that's the logic that pushes both players to defect, leaving them both with nothing, when they could have just cooperated and both walked away with a reward. So the big question is, how do you break that cycle? Well, for a long time, the answer was basically to fight complexity with, well, even more complexity. Let's take a look at why that old way was just so fragile. Yeah, the old approach was all about some really heavy engineering. We're talking about using these complex techniques like shaping gradients, which is basically just a fancy way of saying you're carefully holding the AI's hand through its learning process. Or you'd create this rigid structure with a meta learner calling all the shots and a naive learner that just does what it's told. The problem is, these systems were super brittle. Why? Because they relied on all these hard-coded ideas about what the opponent was going to do. And wow, when you put them side by side, the difference is just night and day. The old way, rigid, complicated, super specialized. The new approach we're about to dig into is the total opposite. It's simple, it's flexible, and it just throws out all that complex machinery. Which brings us to the heart of this really cool paper from Google's Paradigms of Intelligence team. They came up with a solution that is, honestly, it's almost deceptively simple. They just asked a really simple question. What if we stop trying to make the AI agent itself more and more complex, and instead we just focus on the world it learns in? What if the secret to cooperation isn't a better algorithm, but a better classroom? And the technique they use is called mixed pool training. It's pretty straightforward. Instead of training an agent against just one type of opponent over and over, they throw it into this really diverse pool. So half the time it's playing against another learning agent, just like itself. But the other half of the time it's up against a whole bunch of simpler agents with these fixed, predictable strategies. And this is the crucial part. It never gets told who it's playing against. It has to figure it out. So what happens when you do this? Well, the results are pretty amazing. The researchers found that this diverse environment creates this natural three-step process, something they call the extortion pipeline. Yeah, the path to cooperation is kind of weird. It starts with adaptability, then it moves into this phase where the agents are actually vulnerable to being, well, extorted, and then, believe it or not, that very vulnerability is what pushes them towards working together. Okay, let's break down how each step leads to the next one. First up, adaptability. Because the agent has to go up against this huge variety of opponents, and it gets 0 hints, it's forced to get really, really good at figuring out its opponent's strategy on the fly, right in the middle of the game. It becomes what the paper calls an in-context learner, which is basically just an expert at reading the room and changing its team plan instantly. Okay, but here's the twist. That amazing adaptability, it actually becomes a predictable weakness. Since the agent is so good at responding to what its opponent does, another smart agent can learn to totally manipulate those responses. It can, in effect, extort the adaptable agent, forcing it into an unfair deal just to maximize its own score. So this is the key. What happens when two of these super sophisticated extortion learning agents go head-to-head? Well, they both try to manipulate and extort the other one. And what happens is their attempts to get an unfair advantage just cancel each other out. And the most stable, most rewarding strategy that's left for both of them in the long run is just to cooperate. Simple as that. It's a really beautiful theory, right? But does it actually work in the real world? Let's check out the data. And this chart just lays it all out perfectly. Look at that bar on the left for mixed opponents. You can see cooperation levels are way, way up. Now, look at the other two. When the agents were only trained against other learners like themselves, or get this, when they were told who they were playing against right from the start, cooperation just totally tanks. They go right back to defecting every time. So the takeaway here is crystal clear. High levels of cooperation only happen when you have this combination of diversity and uncertainty. You absolutely need both. A diverse pool of opponents, and the agent has to figure out who it's playing against on its own. You take away either one of those things, and boom, the cooperation just vanishes.
Now, this is way more than just a clever trick to win a simple game. This finding has some really profound implications for how we even think about building cooperative AI systems down the road.
What this research really gives us is a simple, scalable blueprint for creating AI teamwork. It shows us that we might not need some central controller or a bunch of complex top-down rules to force AIs to cooperate. It can just emerge naturally from the bottom up.
So why is this such a big deal? Well, a few reasons. First, this whole approach is a perfect fit for modern AI, like foundation models, because they're already designed to be these powerful in-context learners. Second, it just uses standard decentralized training, which means it's pretty easy to scale up. And finally, it's just this powerful demonstration of emergence, how a really complex and desirable social behavior can pop up from some pretty simple environmental conditions.
The authors of the paper put it best themselves. This isn't just some interesting little finding. They call it a scalable path for the emergence of cooperative social behaviors. That's a huge deal. It's a fundamental shift in how we might approach AI alignment and getting AIs to work together. Which really leaves us with a final kind of provocative thought. Just by creating a diverse and uncertain environment, these totally selfish agents learned the pretty sophisticated social skill of cooperation. It really makes you wonder, what other human-like social behaviors are just sitting there, waiting for the right kind of classroom to emerge all on their own?